All right. Welcome to Introduction to CP/M Programming. As the sign says, it's a brief history of the hardware and software development tools for CP/M. So today, we'll be covering a few things. The introduction to 8-bit microprocessors, just a brief history to get everybody on the same page. This crowd probably knows most of this, but I published this first on a blog to the rest of the world, and they don't all know what we know. And then we'll go over, the brief history of CP/M. I really want this there. Programming languages is the meat of it, and then some modern tools, for dealing with CP/M on current equipment. So first, the introduction to 8-bit microprocessors. This is the brief thing. We got the Intel processors, the Motorola, the MOS Technologies, and Zilog. The first one is the 8008. It was the first of the 8-bit microprocessors. It really suffered in that it only had 18 pins. So your 8 main pins for data and address at high and low were triple multiplexed. So it would have up to 30 components just to interface it with the RAM. And if you've done, if you've done any of the 8-bit Ben Eater stuff and the concept of the memory address register, it was the latches that this chip required in order to get it to work. And then from there we get the 8080, which was the original workhorse. This one was actually usable. The designer for this, I can use this paper. It was crucial to computers like the Atari 8800, the Altair 8800, and the MSI, and others. So then, Motorola came up with the 6800, which was, a similar processor, but it was completely designed from the ground up to be different. So it had, a smaller number of registers and a more orthogonal instruction set, so that, an instruction would do things with different types of memory access. It still was the same instruction. You see a lot of that in the mini computers like the PDP-11. One instruction's got 5 addressing modes. The 6800 is a lot like that. The 6800, the biggest machine that it early came out with was the Southwestern Technical Products Corporation's 6800. It was one of the first computers based on that processor. Then we get to the 6502. When it was introduced in 75, it was the least expensive processor on the market. The difference between like $300 and $25 per unit. And so it found its way into a lot of stuff. The Apples, the Atari 8-bits, the BBC Micro, the PEC, the VIC-20, and the Commodore 64 to begin. And it was also in the Atari 2600 game machine. So then we get to the Z80, which is the biggest one for what I'm talking about. It was binary compatible with the 8080, but it also had an enhanced instruction set, a duplicate set of shadow registers, so that you had 2 full sets of the 8 and 16-bit registers. And some of the additional instructions would do block copy and searches. So then we go into our brief history of CP/M. Now, it originally started out as the control program monitor, and later it was called the control program for microcomputers. It was a mass market operating system created in '74 for the Intel 8080, 8085 systems. Gary Kildall from Digital Research wrote it while he was in grad school. He wrote it for a friend that was working on the 8080 development system. And it was as an operating system to run on the Intellect 8 development system, equipped with the Shugart Associates 8-inch floppy drive, interfaced via a custom floppy disk controller. It was written in his own language, PL/M, programming language for microcomputers. Yeah, you see the, yeah. It was, the same kind of naming convention that IBM uses for their PL1 and so on. He developed it on the Digital Equipment Corporation's DEC System 10 under TOPS 10 operating system. And so it has incorporated in its design some of the same functionality that you find there. It's where you get PIP. The Peripheral Interchange Program is directly lifted out of that environment. CPM supported a wide range of microcomputers based on the 8080 and the Z80, and has been ported to several other computers in the process. From CPM, they did MPM, which was a multi-user version. They also got CPM3, which then took some of the features out of MPM and ported them back into the CPM single-user line, giving you bank switching and scheduled I/O, so that you get a little better control and use of the system, so that you can use more than 64K of RAM with the bank switching. Yeah, CPM eventually became the de facto standard as the dominant operating system for microcomputers in combination with the S100 bus computers. This computer platform was widely used in business throughout the late 70s and into the early mid-80s. I used Kpros for one of my first jobs out of school, and doing CPM development, and that was always a lot of fun. And as I said, the operating system was described as a software bus, allowing multiple programs to interact with the computer hardware in a standard way. Programs written for CPM were typically portable from one system to another, usually just needing to be recompiled and then tweaked for whatever control codes were necessary for whatever displays or printers you were using. And a lot of, WordStar, VisiCalc, not VisiCalc per se, but its predecessor, were all done on CPM systems originally. The restriction on portability for systems that were developed with Z80s, you couldn't run those on 8080s. But that was because they would use the incentive instructions and they just weren't available. Another was the graphics routines, especially in games and graphics programs, because those were always, you wrote directly to the hardware. They weren't interfaced in through the BIOS. CPM increased the market share for both hardware and software, greatly reducing the amount of programming required to port an application to a new new manufacturer's computer. Yeah, I got ahead of myself. Many different companies produced CPM-based computers for many different markets. InfoWorld stated that CPM was well on its way to establishing itself as a small computer operating system. Even companies with proprietary operating systems, such as the Heath Zenith HDOS, offered CPM as an alternative for their 8080 Z80-based systems. This one gets deep. We're talking about what's going on with CPM. How is it built? What does it do? I can say that the blog actually goes into a lot more detail. I'm going to throw away all the pages that we've skimmed over. CPM is, like I said, is the monitor and control program for microcomputer systems that uses a floppy disk or a Winchester hard disk as backup storage, used on computers based on the 8080 or Z80 computer. The CPM monitor provides rapid access to programs through a comprehensive management package. The file system supports a named structure allowing dynamic allocation of file space, as well as sequential and random access. Using this file system, large programs can be stored both in source and machine code. CP/M2 was a high-performance single-console operating system that user table-driven techniques allowed field reconfiguration to match a wide variety of disk capacities. You get single-density drives, double-density drives, then you get the hard drives. There's a parameter table in the BIOS or in the BDOS that lets you set up the configuration of your hard drive, reassemble that, link it in, burn a new ROM, and you're good to go. Up to 32 megabytes in future releases for the hard drives, which was huge back in the day. My first hard drive was a 20 megabyte drive. CP/M is logically divided. Go back. There we go. CP/M is logically divided into several distinct parts. The BIOS, the basic I/O system, that's the hardware-dependent layer. The BDOS, the basic disk operating system, that's where all of the functionality of CP/M resides. The CPP, the console command processor, that's the user interface. And then, of course, the last chunk of the memory is the transient program area. That's where your programs all go. Too many buttons. There we go. The BIOS provides the primitive operating system support operations necessary to access the disk drives and to interface standard peripherals, teletypes, CRTs, paper tapes, readers, and punches, and user-defined peripherals. You can tailor the peripherals for any particular hardware environment by patching this portion of CP/M. If a computer manufacturer wanted to be able to run CP/M on their hardware, they would have to create a version of the BIOS that understood that hardware. This was the beginning of the concept of the hardware extraction layer. It was never called that back then, but that's what it was, that would allow CP/M to run on so many different pieces of hardware. The BDOS contains all the primitive functions available to CP/M and user programs to deal with the disk drives, keyboards, and screens. It provides the disk management by controlling one or more disk drives containing independent file directories. The BDOS implementation implements disk allocation strategies and provides fully dynamic file structure construction while minimizing head movement access on the disk during access. The BDOS entry points that include the following primitives, which any program can access: search, looks for a particular file by name; open, close, rename, read, write, and select, which lets you change the drive for further operations. Then we get to the CPP. It provides a symbolic interface between your console and the remainder of the CP/M system. The CP/M reads the console device and processes the command, which could include listing file directories, printing the contents of files, and controlling the operation of transient programs such as assemblers, editors, and debuggers. The last segment of the CP/M area is called the transient program area. The TPA holds programs that are loaded from disk under the command of the CCP. During program editing, for example, the TPA holds the CP/M text editor, the machine code, and data areas. Similarly, programs created under CP/M can be checked out by loading and executing these programs in the TPA. Any or all of the CP/M component subsystems can be overwritten by an application. They can be overlaid by the executing program, such as the user program. The TPA can override the command processor. You can get an extra 4K out of that. And when your program exits, you go through the warm boot process, and CP/M just reloads itself, and away it goes. There are two types of commands in CP/M, the built-in commands and the transient commands. The built-in commands are the ones that are actually coded in the CCP. and the CCP doesn't recognize what you've typed, it will look in the directory of the current drive, and if it finds an executable file with that name, it'll run that as if it were a regular command. This way you can extend your operating system by writing a batch of command files, and as long as they're on the current drive. There is no directory structure. There are no subfolders. It's all single-level directory. But what you can do is separate the disk by user number. So if you're user 1, user 0, 1 through 15, yeah. And if you are that user, you can only see the files in your user area. You can't see anybody else's. Built-in commands, they actually mimic some of the, actual functionalities like erase and dir, rename, save, type, and user. Users let you change your user number. Transient commands, these are some of the ones that are actually come with CPM. Stat lets you look at the sizes of files, or how much free space is on the drive, or what user number you're logged in as, that kind of thing. The ASM is the basic 8080 assembler. Load lets you load hex files for execution. DDT is a dynamic debugger. PIP is that peripheral interchange program that lets you move files, lets you copy files from disk to disk, or from user to user. And ED is the default editor. Sysgen lets you create a new CPM system disk. And then submit is their initial batch processor. You can actually create a text file that has commands and references the arguments, and then you run them just like a DOS batch file. Well, it is a DOS batch file. And then dump lets you dump contents of memory, contents of file in hex. And then move CBM lets you regenerate CPM for a particular memory size. CPM is built on how much memory there is, so that things sit in the known places in memory at all times. Minimum of a CPM system would consist of a computer terminal using ASCII characters, an Intel 8080, and the 8085 or a Z80, at least 16K of RAM, beginning at address 0, because those processors always start at 0. A means of bootstrapping the first sector of a disk, either a boot ROM or a bootloader manually entered, and at least one floppy drive. I'm going to go through these. This image shows what we just talked about. How the memory starts out, the BIOS, and then the BDOS, and then the CCP, then the transient program, and then, like everybody, the 0 page. All the important stuff is down in the low memory. Low memory has, the reset vectors, the warm boot vector, the BDOS call vector, a file definition block, which will describe what file you're trying to access in this BDOS call when you're trying to get files out. And get down here so I can actually read that. The first 8 bytes are really important. They are the main boot code. Jump, at address 0 is the jump command to boot the system. That's the cold boot vector. And then the I/O byte describes how your peripherals are set up. What is your punch? What is your reader? What is your console? What is your printer? And that maps those logical names to physical devices. And then the disk byte says, what's my current disk and what's my current user? And then the BDOS system call vector. And then, like I said, going up from there, we get the restart vectors for the various interrupts, the BIOS work area, and then the file control block, and then the file buffer, which is a 128-byte buffer for the a single disk block. When you start a command, the command string that was typed in actually goes there, so that you can reference all of your arguments. And then here's a sample directory entry. It's really straightforward. It's the first byte is let me get my picture here. Yeah, the first byte is EA if it's erased. Otherwise, it's the user number, and then the file name, and then the reference to the actual block it starts at, or a reference to the map that says what are all of the blocks for the random files. Then the file control block looks a lot like a directory entry, except of course it can't be erased. And you populate this with as much or as little information as you've got when you make your system call to access that file. And all of the services that CPM are accessed through the BDOS. The facilities that are available for access by any transient program fall into two general categories: simple device I/O and disk file I/O. Access to the BDOS functions are accompanied by passing a function number and information address through the primary point located usually at boot +5, which is address 005, because you've got the 3 bytes of the initial jump, the 2 bytes of the I/O byte and the disk byte, and then this jump instruction that is the reference into the BDOS. For instance, if a program wants to print the character A, you just do a move immediate of 65 to the A register, 65 being the value of the ASCII value of the uppercase A. And then the BDOS command is 2, so you put that in the C register, and then you call through 005 to get the character printed to the screen, and then when CPM does that or return, you go to the next instruction. So this is the meat and potatoes. This is the, this I need the paper for, because all of my anecdotes I wrote down. I didn't put them in the slide. Like it says, there are many programming languages for CPM. The first was PL/M, the anachronism for Programming Languages for Microcomputers. It's a high-level language that was conceived and developed by Gary Kildall in '73 for Hank Smith at Intel for the 8008, or the 8008. It was later expanded for the new Intel 8080. The 8080 had enough power to run the PL compiler, but lacked a suitable form of mass storage. In an effort to port his language from the PDP-10 to the 8080, Kildall used PLM to write a disk operating system that allowed a floppy to be used. This was the basis for CPM. Assembler has always been the first available programming language for a new processor. With the 8080, people were hand assembling their code and just toggling them in on the opcodes on the front panels to get the programs to run. An assembler and linker, a linker loader, were supplied with CPM. Basic. That's what was going on. Okay, Basic gained popularity, particularly as a program. As a general-purpose programming and educational programming language. CPM came with the Microsoft Basic interpreter in Basic. It was Microsoft. Microsoft wrote the first Basic for microcomputers with the Altair and their 8K Basic. And then they licensed it everywhere. Pascal, known for its structured programming approach, also gained traction on CP/M, providing an alternative to BASIC and assembly for more complex applications. While other languages like Fortran and COBOL were prevalent during the same period, they were more commonly found on the larger computers and not widely used on CP/M. However, Microsoft decided that we needed ports of both of those. So there's a Microsoft COBOL compiler and a Microsoft Fortran compiler. Assembly language remained crucial for the close-to-hardware tasks, while BASIC and Pascal offered more user-friendly programming environments for general applications. While other languages like Fortran and COBOL were prevalent, I just hit the button. It would be a large undertaking to discuss all of the languages that CP/M, used in CP/M development. The ones I'm going to cover today are Assembler, BASIC, Pascal, and C. I'll give a brief history, mostly pulled from Wikipedia, because, why not? Follow up with some, personal observations because I've used all of these, and then we'll show an example of a Hello World program in that language. Now, in the slides, I've got snapshots from all of those, but I also have a pocket computer that's running a Z180 and CP/M that I did all of these examples on, and we can go through and show them live when I set up back there if we want to. Additionally, there are some other languages that have been archived and made available, including PLM, Microsoft's Fortran and COBOL, Turbo Modula, APL2, Forth, Lisp, and SLR. I didn't even know what SLR was when I started. I still don't, but it was on Wikipedia, so I included it. All right. Assembly language. In computer programming, assembly languages, or assembler, or symbolic machine code are often referred as simply assembly, and commonly abbreviated as ASM, is the low-level programming language with a very strong correspondence to the instructions and the architecture of the machine code. Assembly languages usually have a one statement per machine instruction, but constants, comments, and directives, symbols, labels, etc., are generally also supported. Because the assembler depends on machine code instructions, each assembly language is specific to a particular computer architecture. Sometimes there's even more than one assembly language for the same architecture, and sometimes an assembler is specific to an operating system or to a particular family of operating systems. Most assembly languages do not provide specific syntax for operating system calls, and most languages can be used universally with any operating system, as the language provides access to all the real abilities of the processor on which they're running. In contrast to assembly language, most high-level programming languages are generally portable across multiple architectures, but require interpreting or compiling a much more complicated task than assembling. And then we have our first Hello World program. It starts out with an origin of 100, which is where the start of the TPA is, sets up a couple of constants to access the BDOS and the boot vector. And like the sample we saw earlier, this one copies the BDOS request print string into the C register, loads the D register up with the address of the string to print, calls the BDOS, and then jumps to the boot vector to go back to CP/M. And the message is, a new line feed, hello world from CP/M, and another new line feed, return in line feed.
That dollar symbol, is that the string terminator in CP/M?
Yep. Well, in this assembler, it is the string terminator, and CP/M requires it for this system call. So it really is the string terminator for CP/M.
If it wasn't there, I assume the machine would just dump memory and it'll crack?
until it, you know, till it ran into one. You know, buffer overflows. It's just like the null terminated C string. You know, basic. You know, beginners all-purpose symbolic instruction code. BASIC is a family of general-purpose, high-level programming languages designed for ease of use. The original version was created at Dartmouth College in 1963. The first microcomputer version was co-written by Bill Gates, Paul Allen, and Monte Davidoff for their newly formed company Microsoft, and was released by MITS in punch tape for the Altair 8080 shortly after the machine itself, immediately cementing BASIC as the primary language for early microcomputers. Microsoft sold a CP/M BASIC compiler known as BASCOM, which was similar to source language to MBASIC, their BASIC interpreter. Programs debugged under MBASIC could be compiled with BASCOM, and you know, since the program text was no longer in memory, the runtime elements of the compiler were smaller, and they were smaller than the interpreter, then more memory was available for the user data. Speed of real program execution could be increased by up to threefold just by compiling it.
Now, was that really a compiler, or was it just a...
It was a compiler.
But actually, it actually generated a machine?
Yeah. Yeah.
Because under DOS, there was a program called BASCOM, which
It would pre-interpret.
It would just embed the interpreter and the bytecode.
Right.
Okay.
But this generated it generates a COM file. There is a BAS run. Will run the bytecode directly, but anyway, this one is a looped version. Growing up in the 70s, the BASIC that I first was exposed to was the BASIC on an HP 9830 calculator computer. The local university had one in one of the physics labs with a flat-bedded plotter attached to it. And I don't remember exactly how I got access to it, but I had a cassette tape that had all my programs on it. And I got to, I got the plotter to draw an enterprise just by, graphing it out and then putting in a list of numbers and data statements and saying, pen down, plot here. I was elated back then. It also had a small terminal program. That calculator had like a 3-line Pixelplasma, and it was connected to the local the university's PDP 1140, which was running Ristus. So then I had access to Basic Plus, and then the high schools in the county all had dial-up access to that computer on a 110 ASR 33 teletype with an acoustic coupler. Because of that, I learned to type because that was just too slow. Professionally, MBASIC on CP/M, GW Basic, and QBasic on DOS were pretty much all I had. All I ever had to do. I had a little bit of Visual Basic, and of course VBA inside of Excel, but nothing. A lot of BASIC after that. So the example here is like I say, is a looped program, just for I equals 1 to 10, print the message and the I so that we know how many times we did it. And then we loop through, we get all 10, and then we take the same text file and we run it through BASCOM, and then we link it. This is how I know it's an actual executable. And we're not linking in a runtime with it. We're just linking it, and the linker identifies the execution point that we told it up in the assembler to generate, and then we just run the same code again. It runs much faster as a compile, but it generates the same output. The next language we look at is Pascal. That one was a lot of fun. Pascal is an imperative procedural programming language designed by Nicholas Wirth as a small, efficient language intended to encourage good programming practices using structured programming and data structures. It is named after the French mathematician, philosopher, and physicist Blaise Pascal. Pascal became very successful in the 70s, notably in the burgeoning mini-computer market. Compilers were also available for many microcomputers as the field emerged in the late 70s. It was widely used as a teaching language in university-level programming courses in the 80s. Yeah. Yeah, we have it. The Pascal we used was actually on a mainframe, and we were still doing punch cards then. So, but then we got USCD Pascal on our Apples, and but we didn't have many of those. So the professors had those. UCSD. I can't say words. The Pascal, Borland came out with Turbo Pascal, and that one was hugely popular due to the aggressive pricing strategy, one of the first full-screen IDEs, and very fast turnaround, just seconds to compile, link, and run. It was written highly optimized assembly language, making it smaller and faster than much of its competition. And not having to swap floppy disks when you're running it and getting your source to execute was wonderful on the K-Pros. Just load and go. The object Pascal that I was talking about, that talks about in the first paragraph, winds up being Delphi in Windows, and I used that one professionally at the Learning Company to develop software for educational software development. We used it to manage grammars for a speech recognition package. I used Turbo Pascal on CP/M back in the day, and then again under Unix, a company was developing a software medical billing package that was written on top of a Windows library that they had that allowed them to do multi-user, multi-processing on their little wacky computers that they could share memory on. And then I wrote a plugin for that would access IBM formatted records for the IDC9 codes and get the appropriate billing flags set for it. The example here doesn't show much because you just start Turbo Pascal and it goes. But yeah, this one as you can see, it's a very short program. It makes a call to one of the libraries that comes with Turbo Pascal to clear the screen, and then just like the other programs, it sets up a simple loop from 1 to 10 and prints out the hello from Pascal, lines 1 through 10. The C is a general purpose programming language that was created in the 70s by Dennis Ritchie and remains very widely used and influential. By design, C features cleanly reflect the capabilities of the target CPUs. It's found lasting use in operating system code, especially kernels, device drivers, and protocol stacks. C, actually, if you look at the operators in C, they actually map fairly well one-to-one to the PDP instruction set and its addressing modes because, well, that's what it was built on. Like Pascal, it's an imperative procedural language, supporting structured programming, lexical variable scopes, and recursion, and a static type system. It was designed to be compiled and to provide low language access to memory and language constructs that map efficiently to the machine instructions, with minimal runtime support. Despite its low-level capabilities, the language is designed to encourage cross-platform programming. A standards-compliant C program written with portability in mind can be compiled for a wide variety of computer platforms and operating systems with few changes in the source code. I ran into C in college while working as a computer lab assistant. I ran across a DECAS tape, a Digital Equipment Corporation User Society tape, that had a C compiler that would reportedly run under our operating systems, one of the subsystems that it had. I got permissions to load the tape and copy the compiler sources in the make files. The compiler was written in Macro 11, and while it compiled, it did not generate runnable code. A 2-week journey into the code, and I discovered that a piece of the code generator was producing malformed assembly code. Correcting the problem and getting the compiler where it got me extra credit in my compiler class, which was nice. I would run into C again and again in various Unix systems over the years, including CP/M, DOS, Windows, Unix, and Linux. Even now, I'm still writing C and C++ applications. The sample program, like the others, is a looped version of the classic Hello World program. It'll be using the Manx Software Systems Aztec C compiler. And this compiler is fairly faithful to the original KNR C. Later, high-tech C would come out and be more ANSI compliant. And this again is a simple one. For I equals 1 while I is less than 10, I increment at the end of the loops. Print hello world from Aztec C with an integer and pass I as the argument. And the Aztec C is a 3-step process. You compile the C, which generates assembly. You assemble the assembly, and then you link it, adding in the C library, runtime library, and then run the program, and it generates the listings 1 to 10. And I also have examples of this in Fortran and COBOL, because why not? But I didn't include them in the slideshow. But they're in the original talk, the original notes for this. Modern CP/M tools. Modern tools related to CP/M primarily involve emulators and utilities for interacting with CP/M systems and files. There are many modern ways to experience CP/M. There is modern hardware. Still, systems are being produced that can run CP/M. I've got references in this talk to several places where you can pick up systems. There are emulators all over the place that allow you to run CP/M in your favorite modern environments. And then there are utilities that run on Windows, Linux, and Mac OS that allow you to manage disk images that are compatible with the emulators and with proper equipment, the actual hardware. There are several new Z80 machines out there. Small Computer Central has 3 different varieties. A modular backplane with cards, and the backplane comes in 3 sizes. An expandable single-board computer, a motherboard with slots that you can plug in stuff, and a non-expandable single-board computer. There's a good ROM BIOS out there from ROM BWB. This is a customizable and can even have a bootable system disk in the ROM image. The project also has a large selection of CP/M software packaged as disk images. I'm using the SC131 Z180 pocket computer today to run all of the examples that I showed in this. They're all screen caps from running it on that system. CPUville, designing and building and selling obsolete computers for educational purposes since 2004, also has a Z80 computer kit and accessories that can run CPM when fully built out. There are even GitHub repositories with new Z180 systems being designed, such as Yaz 180. Yet another Z180, and all of the Gerbers and everything you need to build that are in the GitHub repository. And sorry I didn't follow the slides. I'll let them sit for just a second. As far as emulators, there are several good emulators out there. And the ones I work for for this presentation all run under Linux and Windows and Mac OS, with the exception of CBM EMU, which only supports Linux. It's made for building a CPM machine, runs on a Raspberry Pi. ZPack is my favorite. It's Z80 and Intel 8080 cross-development package. It actually is the heart of the High Nibbles MSI 8080 emulation hardware. He's running ZPack inside of that on an ESP32. The virtual computer system is CPM 1, 2, 3, and NPM 2 completely from the sources. You download the GitHub repository, do a make, and you've got all of those emulators right there ready to go. It even compiles with SDL2 so that you get good graphic emulation for the front panels on some of the systems as well. And then that's a screenshot from just straight out of the simulator. I've got that simulator running on one of the other laptops back there. The next one was Run CPM. It's an application that executes finished CPM programs on many modern hardware, including the Arduino Due, which is what they're running on that Altair back there. The CPEMU is a CPM 2.2 emulator. That's all it does. It doesn't implement the it's not a hardware emulator that runs CPM. It's an actual CPM emulator. It does not implement a specific set of terminal control sequences. Instead, it just sends everything straight out to the console. The installation steps you through everything. You can run it. You can build a native on top of a Raspberry Pi without running any Raspberry Pi OS, which is the one thing it does. Wait a second. Lordy. Two-sided paper gets me again. OpenSimH. That's a general purpose simulator. You can actually simulate a whole bunch of hardware with that. PDP-11s, data generals, but it also does Z80s and 8080s. And I did a Z80 emulation here with just a small CPM disk. Didn't do a lot with it. And then, like I said, then the CPM EMU, all I did was just bring that up to see that it worked. Didn't actually do anything with it. The utilities. Two major allow you to access the system disk and cross-compile. CPM Tools is a package that lets you access CPM file systems. It reads and writes image files. You can list the files out of them. You can copy files to and from a CPM system. You can remove files from them. You can change their attributes, so on and so forth. You can even make brand new CPM file systems that you can then are suitable for doing images to physical media or passing straight into an emulator. And all of these emulators can read and write these file systems, so it makes it easy to put together a custom image. ZPack's built around those, and they actually have a makefile system that makes it very easy to build custom images. You just lay them out in a directory with the user numbers and run their script, and it'll spit out an image file in floppy disk format or hard disk formats up to 8K or 8 meg. Yeah, 8K. Small image, small hard drives. And then the best cross compiler I found is the ZXCC, and it runs it emulates enough of of a Z80 system to allow you to run the high-tech C compiler along with the basic assembler, relocatable assembler, and the linkers, so that you can spit out Z80 and 8080 compatible code in a modern environment. A lot of the functionality is wrapped up in two separate libraries, CPM-IO and CPM Reader. The CPM Reader is really handy because it allows you to interface your local file system to the CPM environment, and so that your local hard drive appears to be as a CPM drive, but only the current whatever directory you're running it against. The author of this system also has does it say what it is? Yes, yeah. He was saying that CPM Reader is also used for the Joyce PCW emulator, so that it has full access to the local hard drive inside its emulation. The main features of CPM-IO is that it's a multiple terminal emulation. It does VT52, VT100, and then native ANSI. So, in summary, CPM was a leap forward at its time. It was one of the first commercial disk operating systems, and it's found its way into a large number of computers. Some of the top business application software started on CPM. There are many programming languages developed for CPM, and the research for this talk brought back so many memories. And at this point, I can open it up to question and answer, and that QR code links to the GitHub repository that supported this talk. It's got all of the URL, all of the sites that I referenced, organized, and along with several PDF files that I had to dig up that, how to use ED, the DDT commands, Programmer's Guide for CPM 2.2, porting CPM for CPM 1.4 version to 2.2, that kind of stuff. But at this point, if there are any questions. The slide deck and the underlying talk are both on that GitHub repository. The GitHub repository also has a link to the blog posts. I had like 10 of them, the different sections of this. I posted them up over the course of 2.5, 3 months from April to June. You're welcome.